Hi, welcome to our first hands-on tutorial. In this tutorial, we're going to cover AutoML with tabular data, which is arguably the most common data type encountered in machine learning today. In this tutorial, we're going to show you how easily you can use AutoGluon for classification and regression problems with data stored in tables, where the goal is to predict one column of values based on the values measured in the other columns. Before we begin, please follow the setup instructions and make sure everything's properly installed. You can actually run this tutorial and all the other tabular data tutorials on your own Mac laptop because they're not that computationally intensive. We're going to just give a quick overview of what AutoGluon can do and how you can access its basic functionality. Here we're going to give the example of a data set of diabetes patients from a hospital where they recorded various medical features and information about each patient. The link to the original data set is here. First, we're going to import AutoGluon and specify that our task of interest is what's called tabular prediction. AutoGluon offers a number of built-in tasks that basically allow you to train models for specific data types with just one line of code. Throughout these tutorials, we're going to specify a small subsample of the data only because we want to make sure these tutorials run really quickly for you to just try out. If you want to actually see what kind of performance you would realistically obtain, please set this to a much larger value or just don't subsample the data at all. Now let's load the data. Here we specify that the data lives at this path, which actually in this case is a cloud storage bucket in S3. However, this could just be a local CSV file on your own computer. For example, here's what the CSV file actually looks like. Here we have, various columns, various rows representing patients, and we see that the CSV data is pretty messy, containing strings, numbers, missing values, etc. It's not really suited for most machine learning models. That said, we can load the data via this command, which produces this trained data object that is essentially just a pandas data frame with maybe some additional functionality. We can call head on this object to just keep the first 600 patients data only. And then we'll show just the first 5 rows of the data frame. So this is the data from the first 5 patients. There's 47 columns in this data frame. The original data frame had 60,000 rows, but again, we're only going to be working with 600 of these rows in this tutorial to make sure it runs quickly. And you can see the data contain various features measured in these patients, like their age, weight, what kind of medications they were given, as well as whether or not they were readmitted to the hospital after this visit. So again, each row in the table corresponds to one data point, in this case one patient, where we want to produce predictions in the future for new data points or new patients. Each column is one variable or feature. And so what's really important is that these rows remain statistically independent. That is, you can't have data that, say, is time-based, where values in future times depend on values in previous times. That's called time series data and will not be considered in this tutorial. We're just focused on standard supervised learnings, particularly classification and regression. Here, our goal will be to use these features to predict whether each patient will be readmitted to the hospital or not within 30 days, after 30 days, or not at all. And this, as I said before, is recorded in the readmitted column. Here we can look at some statistics of the readmitted column. We can see in our data set of 600 values, there's 300 values that are no, 300 values that are above 30, and 51 values that are less than 30, meaning the patients were readmitted to the hospital within 30 days after this stay, which is obviously a suboptimal outcome. Now we can apply AutoGluon to this multi-class classification problem. In this case, the multi-class problem actually has 3 possible classes. Here's how we do it. First, we're going to specify a folder where we want to store our trained models. Next, we call task.fit, and we point it to the training data, as well as which column contains the target values that we actually want to predict. This is all we have to do, and AutoGluon will start training models. Here we can see that it's starting training. It found there's 3 unique label values in the target column. It infers the prediction problem is a multi-class classification problem because there's these 3 unique values only. It tells you can optionally change this via certain arguments. It pre-processes the data, and then it decides that the evaluation metric of interest should be accuracy because you didn't specify anything. And then it'll start fitting models. So it'll fit some random forest models, some k-nearest neighbors, some neural network, etc. And then it completes training here. Now we can load a separate data of some new patients. This is typically referred to as the test data in machine learning. It's imperative that you don't load the test data ahead of time to make sure you're not cheating. It's the only unbiased way to evaluate AutoML systems is to only load the test data at the point where you're going to use them to produce predictions and they've already been trained and you're just trying to get a score on how well they do on future data. Again, we can point AutoGluon to an S3 file that's just a CSV file. This could again just be on your local machine, and it will load what is again just essentially a pandas data frame object. Here we subsample the data just to make sure everything runs quicker. We extract the target column values here, that's yTest, and then we drop the target column from the test data just to prove we're not cheating. And here we'll show again just the top few patients' data in the test data set. And here you see they have all the same features as in the training data, but there's no target column information. Now let's use AutoGluon's train classifier to make predictions on the new patients and evaluate how well it was actually able to predict whether or not each patient needed to be readmitted to the hospital after their stay. Here we first reload the predictor object from the output directory that was previously specified during task.fit. This is actually unnecessary here because we're still in the same Python session, but it just shows you how you would do this if you wanted to produce predictions in a new Python session. Maybe you're deploying your models on some separate server. Next, we call predictor.predict on the unlabeled test data frame to actually obtain predictions that we store in ypred. And finally, we evaluate these predictions against the ground truth target values stored in yTest. And here we specify that some auxiliary metrics should be computed as well. And so the evaluation looks like this. The primary metric of interest is accuracy, which AutoGluon just chose by default for multi-class classification. And in this case, it's 52% accurate on our 3-class classification problem. And then it also computed a bunch of auxiliary metrics, including the balanced accuracy, the Matthews coefficient, as well as some per class metrics like the precision and recall for each class, as well as how many test data points belong to that class. And so here you can see AutoGluon struggles to predict the under 30 class because there's just much less data from that class in general. Its precision and recall are much worse than for the other classes. Again, this is just a tiny data set, so you should really run AutoGluon with a larger subsample size to get meaningful performance numbers. Finally, we can print all 600 predictions themselves, and you can see that these really just look exactly like values you would find inside the target column of the training data. Now let's switch gears slightly and go to a regression problem, where the goal is to predict numerical values rather than discrete classes. Here we'll consider predicting the time in hospital variable based on the other features values. This variable measures how long each patient ended up staying in the hospital in days. Here we show a histogram of the distribution of values in this column. And again, we just call task.fit to produce a predictor. We don't need to specify regression or anything like that. Here we just provide the training data, a new output directory where we want to store this new predictor. We specify which is the new target column. And another thing that's different here is we specify time limits for AutoGluon. We tell it should only run for 30 seconds, and within 30 seconds be able to be ready to produce predictions. Finally, we evaluate the resulting trained predictor on the test data. Here we show a shorthand method, evaluate, that takes in labeled test data in this case and internally we'll call predict and score. Now let's look at the output logs from this run. So again, AutoGluon first looks at the label values in the target column, and it shows the first 10 of these values look like this. And AutoGluon then decides that the prediction problem should be regression because this is a floating point, these are floating point values, and there's many unique values observed in this target column. It tells you you can specify, you can override this guess, which you probably should if you already know what kind of prediction problem you have. Next, it pre-processes the data and decides that it's going to evaluate performance using the default metric for regression, which in AutoGluon is root mean squared error. Then it splits the data into training and validation sets, and will start training various models on the training set and reporting some internal metrics on the validation sets. Finally, so it'll train, models like k-nearest neighbors, light GBM, boosted trees, neural networks, etc. And finally, it'll create a weighted ensemble that combines the predictions from all these models. And here it actually completed training in just 23 seconds, which is less than our 30-second time limit because this data set, again, is just really tiny, only 600 data points. And here, finally, it prints out the resulting performance of the default evaluation metric on the test data, which is root mean squared error, and in this case, it's 2.5. Note that some of these internal metrics printed by AutoGluon are actually negative because internally AutoGluon is always assuming higher metrics values equals better performance. So it flips metrics that are actually losses like root mean squared error to be negative internally. Now let's go back to the original predictor for our three-class multi-class classification problem for predicting the readmitted variable and see what actually happened during fit. So this was a three-class problem, and the default metric AutoGluon chose was accuracy. Again, it'll just automatically guess this or infer this if you don't know or if you don't specify what the metric or the type of prediction problem should be. AutoGluon also infers the type of each feature in addition to the type of prediction problem, basically whether it's a numeric column, is it a categorical column of discrete values, and it'll also automatically handle things like data processing, dealing with missing values, and normalization of numerical values if needed. So here we can look at our trained predictor and see what it, see a summary of what it inferred. So here it guessed the problem type was multi-class once again, and then it guessed the following feature types for each column in the data frame. So categorical features are those that are discrete, assign those like gender and age. Recall age here is actually string intervals of lower bound to upper bound of the patient's age for privacy reasons. Things like the diagnosis, the primary diagnosis, secondary diagnosis, whether or not they were given particular medications, etc. These are all discrete features. The time in hospital variable is a floating point feature in this case. That's actually the target value. And then, or it's not the target value here because we're predicting readmission, remember. So here in this case, this is actually being used as a predictive feature. And then the integer columns include like the number of lab procedures the patient received during their stay in the hospital, the number of medications they were given, the number of diagnoses they got, as well as the number of previous outpatient visits they had. And so internally in FIT, AutoGluon automatically chooses a random training validation split of the data if you don't specify anything. The validation data will be separated from the training data and used to score each model and possibly some hyperparameter settings in the model. Then AutoGluon trains a bunch of models in sequence, and finally it ensembles their predictions all together, trying to see if the ensemble can actually outperform any of the individual models. Beyond making predictions, the predictor object returned by FIT can be used to summarize what actually happened during the fitting process. Here we can call the fit summary method on this predictor, which will print out a bunch of information. For example, what models were trained during the fitting process, as well as how well each model scored on the validation data. The number of models that we trained, the types of models, what hyperparameters were previously fed into fit by you, as well as some graphical summaries of this information. Here's one of the summaries. This plot, you can mouse over each point, which represents one of the models that was trained, for example, the random forest classifier here, and it'll show you the hyperparameters that that model used, how long it was trained for. On the y-axis, what was its performance on the validation data. On the x-axis, what was its latency on the validation data, meaning how long did it take to produce predictions. So you can see for the cat boost model, for a light GBM model here, for our random forest model here, using the Gini split criterion. And here we see the weighted ensemble model, which combines a bunch of these individual models actually had the best performance on the validation data, which maybe is not surprising. And so let's now evaluate all our models again using the test data, but this time let's evaluate each individual trained model that was produced during fit. And we can do this using the leaderboard function, where here we pass in the labeled test data once again, and the resulting data frame returned by the leaderboard function looks like this. It contains test accuracy of each individual model here. It contains validation accuracies of each individual model. It contains the time it took to produce predictions with this model on the test data, the time it took to produce predictions on the validation data, how long it took to train this individual model, etc. Note that the performance of many models decreased on the test data. For example, the weighted ensemble model here had a very high validation score relatively and a much lower test score. Likewise, the light GBM classifier had a much higher validation accuracy than test accuracy. This is because even though the validation data was held out during the optimization of individual models, certain training decisions are still made based on the validation set, and this leads to slight overfitting. This includes decisions like when to early stop iteratively trained models, like the neural network or gradient boosted trees, as well as how to combine the model's predictions into a single ensemble. The more decisions that we make based on the validation data, the less reliable performance estimates obtained from this data become, particularly if we do extensive hyperparameter tuning. This is why it's really crucial to only present the test data after training is totally complete to obtain an unbiased estimate of the true predictive performance of your system on new data. Also, AutoGluon can be used to predict class probabilities instead of class labels. So here we can call predict proba on the predictor, and the resulting object will look something like this. It'll be a vector of length 3 for each patient, where each entry of the vector basically corresponds to the predicted probability of that particular class according to the AutoGluon's best model. Here, this is useful if you want to gauge, say, the confidence in your predictions. Maybe you want to rank or prioritize patients. For example, maybe you want to look more closely at patients who are predicted to need hospital readmission shortly after this stay. Maybe something went wrong during the previous stay. Or maybe we want to just use a different probability threshold to convert our predicted probabilities into classes. Maybe false positives have a big penalty in some particular application, and therefore you want to use a more conservative threshold when deciding how to convert predicted probabilities into predicted classes. Whenever we call fit, AutoGluon automatically predicts with the model that previously displayed the best validation performance on the validation data. This is almost always the weighted ensemble because AutoGluon constructs this ensemble to combine individual models' predictions in a way that maximizes validation performance. We can instead specify to predict with a particular model like this. Here we're specifying that we should produce predictions for the first 20 rows of the test data using the neural network model only. The kinds of data AutoGluon can handle include files of CSV format where each column is separated by, say, commas or tabs, and the rows are on different lines of the file, as well as column-oriented files stored in Parquet format. These are commonly encountered if you pull data from a database. Also, you can use AutoGluon to data that's already been loaded in Python as a pandas data frame. If you have data from multiple tables, it's important that you first join them into a single table where the rows correspond to statistically independent observations, i.e. data points where the goal will be to produce one prediction for one data point on future data. The columns should correspond to individual features, aka things that are measured in your data, also referred to as variables or covariates. For more information about AutoGluon, please check out the documentation. Here we show the documentation for fit. If you go to the following link, which contains all the information you need to run AutoGluon in your own applications. There's lots of extra arguments you can specify to highly customize the system. In addition, if you want to see more technical information about the AutoGluon system for tabular data, check out this paper, which contains all the technical details as well as extensive benchmarks of AutoGluon's tabular prediction module against other AutoML systems across data from Kaggle and OpenML.